Welcome back to SciByte, everybody, where we explore the mysteries of the infinite universe and all the tools and technology that science is using to get to the bottom of all of it. I am this guy, Jeremy.
And I'm this girl, Heather. Today we're going to be looking at the periodic table, what some of those crazy little symbols mean, what the numbers mean, why it's laid out the way it is, and how it all kind of affects the way they chemically interact with each other.
Now, I want to say right up front that when we started prepping for the show, a lot of people told us to include that link from the Animaniacs, I think it is. That's the periodic table song.
Trying to say,
so check our show notes, and I might even put it at the end of this episode. It's actually pretty educational. I love that stuff. But we ourselves, Heather and I, are not chemists. I actually want to cover that as well up front. So we've done research as best we can to kind of teach you how to read the table, what all the symbols mean, like she said. And but up front, I'd like to give a little bit of a history lesson. I mean, it hasn't been all that long that we've known about atomic structures, has it?
Well, yes and no. The original idea for the fact that we had atoms, or, some tiny little piece of particle that everything's made up of that can't be broken apart, actually came up about 2,500 years ago.
Holy crap.
Yeah.
That's like ancient.
Oh, yeah. The earliest known concept were a teacher and student named Leucippus and Democritus.
Yeah,
I know I horribly butchered those names.
These guys were peers of Aristotle, right?
Yes, they were. And they kind of came up with this idea, like I said, that there was some tiny little element that couldn't be broken down, that everything was made of. Mm-hmm. Except Aristotle said, yeah, right.
Aristotle basically convinced everybody that the planet, the universe, was made up of those four elements that we talked about on a previous SciByte,
Earth,
right?
air, fire, water.
And just the mixture of different amounts of those.
Yeah, various mixtures of those things is what made up everything.
So despite being around this concept, and actually named, Democritus came up with the name atoms.
Yes.
Closely. Anyway, it's like atomos or something like that.
In a different language, essentially.
Right. Despite being around for 2,500 years or so, it really got no traction because Aristotle, being the bigwig that he is, and let's face it, he does deserve some credit for many things that he did, but he screwed the pooch on this one. And he set back science by thousands of years.
Oh, no.
It took until like the 1800s, is that correct?
Yeah.
Before
so
this
the early 1800s for the concept or the idea to really catch its footing again.
And who was the scientist or team that kind of headed that all up?
A man called John Dalton sort of came up with the concept of the idea, kind of. He saw that things interacted in very specific ratios. So much of this plus so much of that, and it was these equal ratios that made him think math can't be that worked out every time if there wasn't something small making it that way. There's got to be something else.
Are you referring to combinations of things like hydrogen and oxygen when they get together and form water? Is that the basis for what he was dealing with?
Yeah, very similarly to two hydrogens and one oxygen come together to make water. Other gases are very similar, where you'll have three of this and two of that come together to make another a different gas. So it's those combinations, and it was all these ratios and numbers that he was seeing, and he's like, there's got to be something else going on there.
So because of those ratios and numbers, he started hypothesizing that the elements are made up of something even smaller?
Yes, that there is something smaller going on. Now, I did say that, you have two hydrogens and one oxygen come together, but he didn't quite make the leap to say that there's two oxygens, that oxygen by itself actually is two elements together as a molecule. And he didn't really see that you could have elements that would sit normally, paired together. So he had a little bit of a problem with that, saying, "Oh, water is just HO."
But fortunately, he wasn't on his own in this. There was other.
No.
There were, in fact, on the timeline, as far as science goes, I'm actually pretty impressed by this. Dalton started his work around 1808, and as soon as 1811, he was already. There was another scientist. I don't have his name in front of me. Avogadro, who is actually pretty well known in chemistry, if I understand correctly, right?
That is correct. Yes.
And he's the guy that came along and basically said, you're on the right path, Dalton, but this is how it actually works. Right?
Yeah, he went through and analyzed how much gas you could have in a specific volume at a certain specific temperature and pressure. And so then he was able to kind of go through and say, well, actually, I think some of these things come together in pairs. And that leap actually got us more accurate numbers on what all these atoms were and how big they were, how much they weighed.
And that is what led to basically finally solidifying the theory that atoms are made up of protons, neutrons, and electrons. in differing amounts, and that's why they come together in certain ways, and that's where the periodic table eventually came from. But before we get to that, I think it's probably a good idea to give kind of a primer. Most of you watching this probably already know, but let's tell everybody real quick just what exactly a proton, electron, and neutron are, and some of their properties.
Sure. Protons are positively charged particles in an atom. They weigh approximately 1 atomic mass unit and are located in the nucleus of the atom on the interior.
So the concept of atomic mass is basically based on the proton.
Yes.
Okay.
Now, in the nucleus, you also have neutrons, which have no charge. They weigh approximately the same amount that a proton does. And it's these combined in the center of an atom that sort of define what kind of an element or isotope you have, isotopic type of element you have.
Okay, so keep that in mind. We'll come back to some of that discussion to clarify that point a little bit later. But before we do, explain electrons real quick, and then we'll start getting into the actual table itself.
The electron is the negatively charged particle in an atom. It orbits the nucleus. But its mass is so much less than any of the other particles. It takes about 1,800 electrons to make the mass of one proton or neutron.
Wow, those things are teensy.
Yeah, they're very tiny, so they're really not included in the weights of any of these, or because there's just so many electrons required to start to get into the weight.
In fact, you were telling me earlier that you can't ever have that many electrons in a single atom.
No.
What's the limit? Is only like 70 something? 72?
I don't recall off the top of my head, but...
Yeah. But it's much lower than thousands, so it's never even accounted
it's not 1,000.
Yeah.
So it's not going to be even the weight of one proton or neutron.
Okay, so we got all the definitions here out of the way.
Yep.
Let's start talking a little bit about the father of the periodic table himself.
Yes.
Forgot his first name, Mendeleev.
Dmitry Mendeleev.
All right.
This Russian dude back in 1868 was able to take the 60 elements that they had. And he's like, there's got to be a better way to deal with all of these. So he starts putting them in order. And he was able to sort of put them in order of increasing mass. And he kind of saw that there was a repeating pattern to them. So he'd go, one, and the next one, the next one. Oh, wait, this one kind of resembles the one back here. So he starts looping them and piling them underneath each other, sort of the basic and the first idea of the periodic table, sort of the grandfather of the periodic table that we see today.
And he's also the one that pioneered the term, or at least used the term to form his periodic table of periodicity, which is the repetition of a pattern, which is, again, that's why he started putting things, wrapping the order around on itself.
Yeah, and why it's called the periodic table of elements. It's literally saying what it is.
Right.
It's a table of all the elements that we know and their repeating pattern.
I always kind of wondered why they got that name. But I think it's important to point out that Mendeleev was wrong. Kind of drastically so. He definitely was the pioneer of the periodic table.
Yes.
He's the one that set the wheels in motion to eventually get to where we are today. But a lot of what he proposed was just way off base. And it took until 1913 with the scientist Henry Moseley, who was doing more research on the atomic weights of individual atoms and things like that, before we were actually able to give rise to what we now know and recognize as the periodic table.
Mm-hmm. Yeah, Mendeleev was ordering it by atomic mass, which was close, but it wasn't quite right. So when Henry Moseley, ordered them by atomic number, just breaking it down to the number of protons in a nucleus, he was able to sort of get it in a little bit better order. Things lined up better. Things were in the correct order.
And it also filled in some of those holes that Mendeleev's table had left behind.
And from other holes that they didn't have elements for yet, they were actually able to sort of predict how big an atom would be, what its characteristics would be, before they even discovered the element itself.
Yeah, because like you just said earlier, when Mendeleev started working on his table, there were only 60 elements. And at this point, at our current periodic table, there's over 100. I think 116, if I recall correctly.
118, I believe.
118. I think it was only 116 when I was in high school. Back in my day.
There were only 116 elements.
That's right. Why don't we now jump with both feet straight into the periodic table itself. This is really going to be the meat of the show. We want to tell you basically, if you haven't known already, I mean, everybody's seen it, right?
Well, yeah.
Everybody would probably even recognize it as a glance as the periodic table. But I think there's a great deal of people out there that might not actually understand how to read it and what all the extra symbols and everything mean. So we're just going to kind of go step by step. There's also a meaning behind the structure of it itself, and we'll explain that as well. But I guess we should start with the most obvious, right? I mean, the big right smack dab in the middle of every one of those boxes on the thing.
It's a big letter or two letters. Smack dab in the middle of every one, telling us what element we're talking about.
Some of these I find really fascinating because they use old terms for some of these elements. Like the only one that I know off the top of my head right now is plumbum is tin, right? And there's also AU stands for gold because I forget augium. Aurum, that's right.
If you've ever looked at these elements, be like, how did they get AU for gold? That seems kind of silly.
Yeah.
It's because they're just using an older version, often the Latin or the Greek form of the word to describe the element.
Right.
Aurum for gold, natrium for sodium, things of that nature.
And I was just pointed out in the chat room that plumbum is lead.
Oh.
I was remembering. Thank you, chat room, for being my third brain.
Good job,
being
chat.
my second. Before we move on from these, I have a question. Is there a specific reason why they're always given either a single capital letter or a capital then a lowercase? I mean, is this...
Well, there's only 26 letters in the alphabet.
That's a good point.
You're going to get to 26 elements, and there has to be only one of each letter. So you'll start having combinations of them, hydrogen H, helium He. You've already used H, so you need another letter.
Right. Boy, I hope we don't discover too many of these things. We'll have to start having three-letter symbols come out. Now, let's move on to the next little fact of all of these. Now, first of all, every periodic table is a little bit different depending on what publication you're reading, where you're seeing it. There's a number of different things that can be contained in any of these boxes.
Yes.
So we're really only going to be covering the ones that are pretty universal.
Yeah,
the symbol being the first one. And the next is a number that almost universally turns up in every one of these. It's a whole number, an integer, that shows up in the corner or the top of every one of these periodic tables. Heather, what exactly does that number stand for?
That is the atomic number of an element. It is equal to the number of protons in its nucleus. That means that every element only has a very specific number of protons. There cannot be any more, there cannot be any less. Add one proton to a carbon, you have nitrogen. Take one proton away from a calcium, you have potassium. It's a different element, depending on how many protons
by definition.
By
there's no way around
definition.
that. Now, how exactly does that atomic number relate to the atomic weight, which you also sometimes see on these tables as usually a decimal number?
It'll go on to 3 to 5 decimal points.
Right. Now,
the atomic number is talking about just the number of protons. Now, the atomic weight is taking in the consideration of the entire mass of the element. Now, remember we said a few minutes ago, electrons make up such a tiny fraction of the weight that they're not really considered when you talk about atomic weight. They're not really put into the calculation.
Because even if you make that atomic weight roll out to 12 decimal places, it's barely going to have an impact on that final digit.
Yeah. So what you do is you take the number of protons and neutrons, but not all elements have the same number of neutrons.
Oh ho!
And we get into isotopes.
Now, an isotope, by definition, is an atom of a particular element that has a different number of neutrons from its standard, right?
It's any particular form that an atom might take.
Oh, okay. Now, one of the most commonly known from this is that there are 3 variants of carbon.
Carbon 12, carbon 13, and carbon 14.
Right, exactly. And those numbers, 12, 13, 14, refer to the number of elements in the, the number of particles in the nucleus. Because carbon is 6. Yes. So the base form is carbon 12. But if it adds 1 extra neutron, it's carbon 13. And if it has 2, it becomes carbon 14, which is awesome. Tell us a little bit about carbon 14 just while we're talking about isotopes here.
People might have heard about carbon 14 when they talk about radioactive carbon dating. What this means is that it's a radioactive element. So it's very unstable. There's not a lot of it, but we know exactly how much of it there is. There's a specific percentage that it indicates in the Earth's crust. So you have a tree. It is a very specific percentage, carbon 14. Now, if you chop it down and you make a chair out of it, or if it dies, that number cannot stay the same. It's going to start decaying. You may have heard of half-life when you get to radioactive elements.
That decay is one of those neutrons becoming a proton.
That is correct.
In essence, and as we said earlier, if you change the number of protons in the nucleus of one of these things, it no longer remains the same element.
It's no longer carbon. Goes to nitrogen.
Right, exactly. So by measuring this decay of carbon-14 into nitrogen, which happens at a steady rate, right?
Yes, it happens at a very specific rate. You lose about half of your carbon-14 every 5,730 years, give or take 40 years.
So it can be used, but it's not incredibly accurate when you're talking about like human lifetimes, right?
No, but it's going to get you really close. I mean, if you have a piece of carved wood, you can take a piece of that and carbon date it and see it has this much carbon, and then you can say it was originally cut down from a tree at this point in time, give or take someone's lifetime. I mean, so you can if you think about it, it's pretty impressive that you can go back 5,000 years and date something to within one person's lifetime. You're like, you know what? It's either that happened sometime in that person's lifetime.
Mm-hmm, absolutely. The fact that science figured out how to do that kind of stuff really boggles the mind. It's incredible. And again, all of this just exists because of sometimes matter gets together in funky ways, and it just can't stay that way. Let's go ahead and move back to the table here, because in addition to the symbols that are frequently on the table, as I mentioned earlier, the table itself has a very distinctive shape. And there are reasons for the placement of everything on there. Like, everybody knows at the top of the periodic table, they've got like a few boxes on one side and then a big empty space and a few boxes on the other side. Mm-hmm. You can't just smash that together to save space on your paper.
Oh, no, you can't.
No, it's arranged in a very specific way for a very specific reason. Now, what I figured I'd do, Heather, here is we'll go through and talk about the individual rows first, and then we'll cover the columns. So those rows of elements are grouped together in a specific manner, and each row, it has one thing in common, right? Why don't you tell us a little bit about that?
Sure. Well, when you're looking across the row, reading from left to right, you're getting the atoms themselves are getting heavier and heavier because you're adding one proton and often, a couple of neutrons every time. So obviously it's getting a little bit heavier each time as you go from left to right. And as you kind of go, just like reading a book, left to right, and then you go down a line, left to right. Similarly, the weight goes up reading it like that, reading it just like a book. But also, what you get with these rows are energy level differences.
Now, the energy levels, correct me if I'm wrong on this, because this is start to get a little beyond my my understanding here, but the energy levels are like those orbits that you usually see drawn around, like in artists' interpretations of atomic structure.
Yeah, where the electrons lie.
Right, and most of you that know, because you probably know science a little bit here, electrons rotate, they orbit at different levels, different distances from the nucleus, based on several different factors.
Yeah, and each orbit or level can only hold so many electrons.
Right.
So the rows themselves are saying, just by counting, it's this row, this many blocks over, you can know how many electrons it has, where they are located.
As a solid example, I just want to give you guys a real firm example here. I'm looking at the table, and let's take calcium, for example, which on the periodic table of elements is located in row 4, column 2. Now, the fact that it's in row 4 means that it has 4 different energy levels, 4 different orbits that its electrons can follow.
And the first 3 are all filled. And then the fact that it's in the second column says that it has 2 out of that outer shell's possible electrons.
Oh, so it's very important to understand that this is very important to chemistry, because one of the reasons that the periodic table is formed the way it is it helps people understand the way that molecules are formed, the way that atoms hook up with one another. And the primary way that that's done, I think the only way that it's done, but I didn't look into this before the show, silly me, is through the hooking up of those outer orbits of their electrons. So when you have something like calcium that only has 2 electrons in its outer orbit, it has a very high chance of being reactive with other elements that can add electrons or can hook in and fill that outer shell of electrons.
Yes. If something is shy 2 electrons to fill its outer orbit, say, then the 2 of them then calcium, who has 2 extras, will fill that orbit, and then that orbit will be completely full for both atoms or both elements. So that's why they'd be extremely happy to go together.
Right. And that is kind of, at one level, that's exactly why they're in columns the way that they are on the periodic table, isn't it?
Yeah. The fact that the column indicates how many electrons in that outer shell it has sort of means that all the elements in a given column act similarly to each other when interacting with other elements.
Now, one important fact to remember is that as we give you guys kind of an overview of how the periodic table is set up, it's important to know that these are just very generalized things. For example, the orbits of electrons, these can get pretty darn freaky. I don't understand how some of these happen, but you were saying that there can be like tube-shaped electron orbits and
sort of teardrop-shaped and in different orientations.
That's too much for me. I'm not a chemist. But suffice it to say that the further you get towards the bottom and towards the right-hand side of the periodic table, the weirder and weirder things can potentially become at that subatomic level. Okay, but away from the bottom right, let's talk a little bit about some of the iconic groups, because that's what these called. These columns, many of them are divided into groups. And like
groups or families, yes.
Yeah, the far right-hand side of the periodic table is the one that I know off the top of my head because I did pay attention in science class occasionally. These are the noble gases.
Yes.
And they're called noble because they're party poopers. They don't get together with anybody, and they're almost completely inert.
As we go to the right, each column indicates that you have more electrons. So that kind of and that ends up meaning that the ones on the far right their outer shell is full. It means they don't really need to interact with anything else. They don't really want to interact with anything else. So they are inert. So that's why you use something, in an inert gas, because it doesn't want to chemically interact with it.
So they use this in like industrial, you mentioned arc welders or to dilute air tanks, oxygen tanks.
Yes.
They do exist in nature in quite abundant states, most of them.
Yes.
Again, towards the top, things get wacky at the bottom. But they can also be created artificially, and that's why they're so handy for scientists. The fact that they have no chemical or very, very low chance of chemically interacting with anything can be, they're a great tool. Yeah. And we know exactly which ones to use because of the periodic table. It is our savior. It puts them all on the right-hand side, and they're just there for you to notice. What are the ones on the far left-hand side of the column?
Those are called alkali metals. These, as indicated by the fact that they're on the far left, they only have one electron in that outer shell. They're really reactive. They really want to interact with anything they can get their little hands on.
I love these because they explode real pretty.
They
in water,
do tend to.
Of all things. Like, if I recall correctly, potassium is one of these, correct?
I believe so.
And if you drop potassium into a petri dish of water, watch the fireworks, but stand back and wear your safety goggles.
Have your goggles.
Maybe it's best just to tell people not to try this at home.
Yeah.
Okay, but some of the things you can try at home are check our show notes. How's that? That's perfectly safe.
There you go.
Perfectly safe for science because we have so many more links. And like I said, there's that really fun periodic table song. In fact, we've got a version in our show notes of Daniel Radcliffe, Harry Potter himself, singing the song. So check that out. It's funny to do. And if you have any more questions about the periodic table, we'd love to look them up for you. There's actually some blokes in the chat room right now that are, I think they must be chemists or they just paid more attention in science class than I did because they've got all the answers. So hopefully if you guys have any more questions, you can either leave them wherever you're watching this. I would actually like to encourage you all to head over to the actual show page that we have at jupiterbroadcasting.com and leave your comments there if you have any there. If you're watching this on YouTube, just check below for a link that says show notes, and that'll take you to that page and you can comment there. It's just easier for all of us to find all the comments on a particular episode if they're all in one happy little place. But if you can't do that, you can always email us.
SciByte at jupiterbroadcasting.com.
That's become your job. Every single episode now you get to say the email address. We also have Twitters. I don't think I'm going to say them this time, just to shake things up. Now, next week's show is a potentially earth-shattering edition of SciByte.
Next week, we're going to be taking a look at near-Earth collisions, the history of actual collisions that have gone on Earth, what's involved, how these things happen.
We actually, we're probably going to look up whatever's known about, like some major craters that are known of that, impact craters that we can already see the evidence of prehistoric impacts or impacts that may have happened during history even. Now, one of the things that prompted this is actually there was a near miss within the last, 5 or 6 months?
I think so.
Where we were almost hit, and scientists didn't know about it until like a couple days beforehand.
There's a lot of stuff out there in space.
Right. So, but we will get into all of that on next week's SciByte. Until then, everybody, I hope we have expanded your brains a little bit with your knowledge of the periodic table, and we'll see you all again next week.
Did you flip to me?
Yep.
Today we're going to be looking at the periodic... I'm sorry, give me a moment.
Kaboom.
Kaboom! Add water to that potassium and run.
Run!
Run for the hills! Unless they're potassium hills.